In this section, we're going to talk about polynomials. So when we talk about a polynomial, we are talking about something that has some very special characteristics. First off, it can be written in this form. Okay, so I want you to notice the form. I've written it in decreasing exponents. N is the exponent here, and that's going to always be a whole number. So those numbers that are in front of the x's, they have to be real numbers. So we're not dealing with imaginary numbers yet. Also, that n has to be a non-negative integer. Okay, so we can't have a -3 as an exponent. We cannot have fractions as an exponent. We can have 0 as an exponent, but they have to be whole numbers or they could be 0. The domain is going to always be all real numbers for a polynomial, which means that we can plug any x value in and we'll get out some kind of y value. When we talk about the degree of the polynomial, it's always going to be whatever that biggest exponent is. The leading coefficient is the number that is in front of the x with the biggest exponent. Now, if we have a 0 polynomial, then we don't have a degree. The 0 polynomial is just a line y equals 0. So that's not a very interesting one. But it doesn't have a degree. Polynomials are really nice because they are smooth and continuous functions. And what that means is that there's no holes and there's no gaps in this function. So you can see here's an example of a polynomial here. This guy's not. We see all kind of problems. There's a gap in here. There's holes in here. There's sharp corners here and here. So that one's just not nice. It is not a polynomial. Polynomials are always going to be smooth and continuous. So let's look at some equations. We want to know, is it a polynomial? If it is, we're going to identify the degree and we're going to identify the leading coefficient. We're going to do both. So if we look at 15, is it a polynomial? The answer is yes. This guy's a polynomial. No problems there. The degree of that polynomial is 3 because that's the biggest exponent we have. The leading coefficient is the number that's in front of that term. And that number is going to be 1. 16. This is a polynomial also. It meets all that criteria. Exponents are whole numbers. They're positive. So we're good. The degree, that biggest exponent, is 4. The leading coefficient is the number that's in front of that term. So that number is going to be 4. 18 is also a polynomial. That's actually a linear function. The degree here, that biggest exponent we have is that 1 that's on that x. The leading coefficient happens to be the slope in this case, and it's -1/2. Now 19 is not a polynomial. We could rewrite this as 1 minus x to the -1. And we can't divide by x here because that introduces domain restrictions. So this guy is not a polynomial. 21 is a polynomial. I'm just kidding. 21 is not a polynomial. The problem is that 3/2 exponent. We can't have fractions as exponents. 22 is not a polynomial. So if we were to rewrite this, square root of x times the square root of x would be x. But we still have domain restrictions from that original problem. Square root of x can be rewritten as x to the 1/2. So we have issues here. Even if we left it in this form, we would still have issues because of those fractional exponents. So this guy's not a polynomial due to that. 24, same thing. Not a polynomial. We're dividing by x. We can never divide by x in a polynomial. And then 25. This guy is a polynomial. So we can talk about the degree and the leading coefficient. Now, if we were to multiply everything out, look at what we have. We have 2 times x minus 1 squared, which is x minus 1 times x minus 1 times x squared plus 1. So if we were to FOIL everything, we would have an x times an x times an x squared, which means we would have an x to the 4th. So this would have a degree 4. The leading coefficient would be that x times x to the 4th. That's the first term, but notice that that would be multiplied by 2. So that leading coefficient here would be 2. Let's talk about power functions. A power function is a monomial function. Monomial means one term of the form ax to the n. A is going to be a real number. N is that's the exponent. Remember, it has to be bigger than 0. We're not going to talk about the 0 polynomial. It's just not very interesting here. So what this is allowing us to do is talk about the end behavior of a function. We're going to say that something like this will resemble the function y equals x to the 4th, 2x to the 4th, because we're going to keep that leading coefficient and we're going to keep that degree. There could be some twists and turns if we were to graph that, but we want to know what's going on with that end behavior, and that's what that power function does, is it equates this major function to some kind of simpler function that we could think about on the ends of the graph. So when we talk about large functions of the absolute value of x, so we're talking about endpoints. So super big, think super small. And what does this resemble? Let's talk about the end behavior test. So the end behavior test determines what's happening on the ends of the graph where x gets really big or really small. And it's always going to resemble that power function there. So let's say we have this function. We have 2x to the 5th plus 3x to the 4th minus x squared plus 5x. And we want to know, what is that power function? Well, that power function is going to be that y equals 2x to the 5th. So this guy, if we were to graph it, and let's just graph it for fun. Let's go to Desmos. So there's our graph. You can see it's got some, wiggles in here. The power function is the function that this is going to resemble on the ends of the graph. So we are saying this is going to resemble y equals 2x to the 5th. Okay, so you can see there's a big difference in the middle. We're not concerned about the middle with the power function. We're concerned about the ends. So as I zoom this out, you can see how that red graph is matching up with that black graph on the ends. And that's what the power function does, is it matches that up on the ends of the graph. So let's talk about the end behavior test. The end behavior test will tell you what the ends of the graph look like. So if the degree is even, and we could always remember this by remembering what some of those parent functions look like y equals x squared. If we look at y equals x squared, that guy looks like that, right? So if that leading coefficient is positive, so if we're thinking about positive x squared, then both of those ends are going to look up. They're going to go up just like x squared would. There could be some twists and turns in here, but we're worried about the ends. So we're worried about those outer sides, those outer pieces. Are they going up or are they going down? So I like to remember this one by remembering what x squared looks like. Now, if we look at negative x squared, notice that leading coefficient is a -1. We know this guy goes down. So that's what would happen here too. That's a good way to help you remember the end behavior if the degree is even, but you have a negative leading coefficient. Both of the ends are going to point down on that case. Now, if the degree is odd, we could think about x cubed. X cubed looks like this. And we're using that positive leading coefficient. So that left-hand side is going to go down. And that right-hand side is going to go up. There could be some twists and turns in here. But the end behavior is going to model really what x cubed looks like on the ends. And then if the degree is odd, but we have a negative leading coefficient, now we have that reflection that we talked about in chapter 2. So it would look like that. So all odd degree polynomials with a negative leading coefficient, that left-hand side would go up, that right-hand side would go down. There could be some twists and turns in here, but all we're worried about here is that end behavior and what it looks like. So let's look at a couple of examples. We want to identify the power function that it's going to resemble and the end behavior. So if we look at that first one, let's say we multiplied everything together. Then we would have a 3 as a leading coefficient, and we would have an x times another x. Eventually, if we multiplied everything out, we would have 3 times an x times an x times an x, which would be a 3x cubed. So there is our power function that we're going to resemble. Now, we have a positive leading coefficient, and we have an odd degree polynomial. So, odd degree polynomial, second line, positive leading coefficient, that end behavior is going to look like this. That left-hand side is going to go down, that right-hand side is going to go up. In 57, let's say we were to kind of expand this a little bit. We would have that. So if we were to multiply everything out, eventually we would have a 3x times x squared times x squared times x squared. So that would be 3x to the 6th. So this is an even degree polynomial with a positive leading coefficient, which means it's going to be this first block in here. So we would expect both ends of this to go up for that end behavior. So now we can talk about turning points. When we talk about turning points, these are really maxes and mins. So that's a place where that graph is going to change from decreasing to increasing or vice versa. Now, if we have a polynomial of degree n, at most, it can have n minus 1 turning points. It's not guaranteed to have that many, but we could figure out the maximum that it could have. So let's think about some of those parent functions. We have y equals x squared. Well, this is a degree 2 polynomial. So at most, it would have 1 turning point. And we know that quadratic looks like this, so it does have that turning point. Now, another parent function we could think about is x cubed. That one's degree 3, so it would have at most 3 minus 1, which is 2 turning points. Now, x cubed doesn't have any turning points. It looks like that S shape. So it doesn't have any. But remember, this is giving us an upper bound. And not every cubic would look like that. Some cubics do have some fun stuff like that going on. And in this case, this guy would have 2 turning points. So remember, this is just an upper bound. To find those turning points, we have to use the features in the calculator to find that maximum. And we talked about going to second trace and finding the maximum value. in an earlier section, so you could do that to find those. If you decide to take calculus, that's one of the things we do in there is we find mins and maxes without using a calculator. So that's a discussion for another fun class that you can take one day. So let's analyze a couple. We have a couple polynomials here and here. We want to figure out the degree and the maximum number of returning points. So if we look at this first one, the degree of this guy is 3. We have a 3 times an x here, and this would give us an x squared. So we would have a 3x cubed. I'm going to go ahead and throw that leading coefficient in also. The leading coefficient would be 3 in this case. The maximum number of returning points is the degree minus 1. So 3 minus 1 is 2. Now, if we were to graph this, we could see exactly how many turning points we have. Just for fun, let's do that. So this one, you can see we do have 3 turning points. Here and then down here. I'm just getting 2 turning points. Here and then here. I'm thinking about the degree. Looking at that next one. Our degree of this polynomial is 6. It's actually the same problem we did above. We have a 3 times x squared, and then this would give us an x squared times an x squared. Okay, I'm just multiplying those first terms together. So that would give us a degree 6. The leading coefficient here is 3 again. The max number of turning points is always the degree minus 1. So 6 minus 1 is 5. Now we need to talk about x-intercepts. So x-intercepts are also called roots or zeros. Your calculator actually calls it zeros. So if we have an x-intercept, and I'm just going to call it r, then r is going to be a solution of the equation f of x is equal to 0. That's actually how we find x-intercepts to begin with. We take that equation and we set it equal to 0, or we say y is equal to 0. And what that means is that r is an x-intercept of that graph, f of x. So then, if x is equal to r, then we can move this r to the other side, which means that x minus r is a factor, which is what that's saying. Now, with the x-intercepts, we can talk about multiplicity. In other words, how many times does that factor happen? And that really tells us something interesting about the graph. So if that factor only happens once, then we say that that has a multiplicity of 1. So if it happens twice, so let's say we have, well, let's go back to 49. We have an x plus 3 quantity squared. That means the x-intercept that would result from that would have a multiplicity of 2, because that term happened, that factor happened 2 times. The multiplicity is tied to how many times the factor happened. Now, if the multiplicity is even, that means the graph's going to touch the x-axis. So we would expect this graph to touch the x-axis at -3. And that's exactly what we saw in that picture. Here's that picture of that one that we were just talking about. Here's -3. Do you see how that graph is touching the axis there? That happens because the multiplicity is an even number. Now, if the multiplicity is odd, that means the graph's going to cross the x-axis there. So here, let's look at that x minus 7. That factor happened 1 time, and 1 is an odd number. So we would expect that graph to cross the axis at that x-intercept that's represented by the factor x minus 7. And you can see it does cross the x-intercept the x-axis there at 7, 0. So the multiplicity is tied to does it cross or touch the x-axis? So you can see in the picture here, we see some things going on. Because these are crossing here and here, then these have to have an odd multiplicity. If it's touching, then that has to have an even multiplicity. So let's look at a few examples. Let's look at 56. So this is nice and factored. So we have this x plus square root of 3 factor happening twice, and this x minus 2 factor happening 4 times. So if we were to find the x-intercepts, we would take this guy and set it equal to 0, which means we would set each of those factors equal to 0. So x plus square root of 3 would be equal to 0. X minus 2 is equal to 0. So one root would be negative square root of 3. This root would be 2. Now, the negative square root of 3 came from this factor, and that factor happened twice. So the multiplicity is 2, and since 2 is even, it's going to touch the x-axis at that x-intercept. The x equals 2 came from that second factor. The multiplicity is 4. 4 is also an even number, so it's going to touch the x-axis there also. So if we were to graph this, we would see this graph touch the x-axis at negative square root of 3 and at 2. That's a great thing to do. You grab your calculator, pause the video, and graph that equation to verify that. Now let's look at 59. So 59, we have 2 factors. There and there. So if we set each of those factors equal to 0, we're going to get x squared is equal to 0, so x is equal to 0. And then we're going to get x squared equals 2, so x is equal to plus and minus square root of 2. So 2 factors are coming out there. So if we look at that, where that 0 came from, it really came from that guy. We could just ignore that negative 2 in front there. You could view that either way. But it came from that x squared. And that x squared is really x times x. So that factor is happening twice, which means the multiplicity is 2. 2 is even, so it's going to touch. Now, what's coming here, this guy could actually be factored a little further. We don't typically see this in other classes, but we could write it this way. It's really a difference of squares. It's just that number's not a very nice number. It's the square root of 2. So, both of those are happening once, which means the multiplicity for each one is 1. So, it's going to cross the x-axis at each one of those x-intercepts. So you can see how that multiplicity is starting to tie into that 0 and what's going on there. Now, given the zeros and the multiplicities, it's possible to find a representative polynomial for the function. Now, this may not be the polynomial, but it's a polynomial that will work. So let's look at this. That first one, I'm going to call this number 1. We want to form a degree 3 polynomial that has zeros of negative 1, 1, and 3. So we're really working kind of backwards here. So we know negative 1 is a root. We know that 1 is a root. And we know that 3 is a root. So then the factor that would result from this, let's move everything to one side. We would add 1 to both sides, so that factor would be x plus 1. The factor that would result from here, we would move that negative 1 over, so we would get x minus 3. And the factor that would result here, if we move that 3 over, would be x minus 3. So there's our polynomial. That one satisfies the criteria given. If we look at 2, same kind of thing, only now we're throwing multiplicity in. So we want to form a polynomial that has a 0 of negative 2. Now this guy's going to have a multiplicity of 2. And we have a 0 of 4 with a multiplicity of 1. So to find the root that correlates to the negative 2, we're going to move that 2 over. So now we're going to have x plus 2. So there's our factor. But since it has a multiplicity of 2, it's going to be squared. To find the factor associated with this, we're going to move that 4 over. That's going to give us an x minus 4. Multiplicity is 1, so we would have a 1 as that exponent. So here is our final answer. Now, we're just assuming that that number that's in front of everything here is a 1. So there's lots of different variations that can happen here. These are the x-intercepts. But remember, there could be vertical stretches and shrinks that go on here. If we put a 7 in front of this, that would satisfy that information also. It doesn't matter what that number would be. It's still going to cross the x-axis at those places and have the multiplicity that's given there. But what if we had a little bit more information? Let's look at this one. I'm going to call this one number 3. Now we're going to construct the polynomial that will work instead of a polynomial that will work. And we want it to have zeros of negative 4 that has a multiplicity of 1, 0 that has a multiplicity of 3, 2 that has a multiplicity of 1. So we're going to end up with a degree 5 polynomial. And we want it to go through this specific point. So we're going to have to find a here. So let's write out what we know. We have a 0 at negative 4. The multiplicity is 1. We have a 0 at 0, where the multiplicity is 3. And we have a 0 at 2 with a multiplicity of 1. So this factor would be x plus 4. This factor would just be x. This factor would be x minus 2. So our polynomial would be x plus 4. Multiplicity is 1, so the exponent would be 1. We have x cubed because the multiplicity is 3. We could say this is x minus 0, which is the same thing as just x. And then we would have an x minus 2, and that would have a multiplicity of 1 also. But we need to know what is that number in front here. And that's where that extra information is going to come in. They're giving us that 0.3378. So they're telling us an x value and a y value. Let's plug it in. So 378's y is equal to a. And I'm going to reorder this. Ax cubed times x plus 4 times x minus 2. So we're going to have a times 3 cubed times 3 plus 4 times 3 minus 2. Let's simplify that right. This is 3 cubed, which is 27. Times 7 times 1. T 27 times 7 is 189. And then if I divide both sides by 189, I'm going to get 2 for a. So the polynomial that satisfies all of this information would be y equals 2x cubed times x plus 4 times x minus 2. There's our final. And then if we look at this last one, number 66, just a picture here, they want us to find a polynomial that may work. So let's look at the zeros. We see that it's crossing the x-axis at 0. It's also crossing. That's important. So then that means the multiplicity has to be odd. But notice that 1 is touching, which means the multiplicity has to be even. But then at 2, it's crossing. So the multiplicity again is odd. So let's see. A factor that would go with this, we can say x minus 0, which is the same thing as x. The factor that goes with that 1 would be x minus 1. The factor that goes with that 2 would be x minus 2. So one polynomial that would work would be y equals x. And we need an odd multiplicity, so we need an odd exponent. I'm going to use 1 as the exponent. And then we're going to have times x minus 1. Now we need an even multiplicity there, so we can choose any even number for the exponent. I'm going to choose 2. And that last factor, x minus 2, has to have an odd multiplicity. So I'm going to choose a 1 there also. So there's a polynomial that would satisfy all of that information. Now, like we said before, we could put any number in front of this. It would still go through those roots. It would just change that vertical stretch or possibly a reflection. And then the last thing we're going to do, we're going to analyze the polynomial. So we're going to go through all this process. So let's look at this one. If we were to multiply everything out, we would end up, and I don't multiply everything out, like for real, but think about what all this is saying, because eventually if you were to multiply everything out, you would be multiplying all of those front terms together. So we would have x times x times x times x, which would be an x to the 4th. So there's your power function. The leading coefficient here is 1. So our power function is y equals 1x to the 4th. Now this is a positive leading coefficient. It has a even exponent. So that in behavior is going to look something like that. Now let's find the x and the y-intercepts. To find an x-intercept, we're going to set this equation equal to 0. So if I set this equal to 0, then I need to set each factor equal to 0. So I'm going to get 2, I'm going to get negative 2, and I'm going to get negative 4. Now that 2 has a multiplicity of 2, and the multiplicity is even, so this is going to touch. At negative 2, that multiplicity is odd, is 1. So it's going to cross. And then 4 is also odd. Has a multiplicity of 1, so it crosses. So it's crossing the x-axis at negative 2 and negative 4 is touching at 2. To find the y-intercept, we're going to set x equal to 0. So when I do that here, be careful. I've seen a lot of mistakes on this over the years. So we're going to have negative 2 squared times 2 times 4. So this is 4 times 2 times 4, which is 32. So there's our y-intercept. Now we need to find the turning points, and we're going to use the calculator to do that. So if you plug this into your calculator, now I'm going to have to use Desmos, otherwise my calculator is going to be sideways. So you can see the x-intercepts here. We know we have a maximum of 3 turning points. It's a degree minus 1, and we have exactly 3 turning points here, here, and here. So to get those values, we're going to have to use the calculator to give us a really good value. So remember, this is where you're going to want to pull your calculator out, go to y equals, type it in, and then use that max min feature. We're going to have a min here and here. That one's happening out of 0. We know that one for sure. And then we're going to have that maximum up here. So it looks like Desmos is giving me a good idea of where those are. So you could verify these in your calculator. Desmos is doing a great job. This is the exact same thing that I got in the calculator. So now what we want to do is we want to take all of this and we want to put it on a graph. So we're going to do that. So I'm going to go down here and I'm just going to draw. This is a quick sketch of what this looks like. I'm going to go by ones on the x-axis. So, and I'm going to go by 5s on the y-axis. So let's plot what we have. We have a y-intercept at 32. So here's 30, 32 would be somewhere in here. We have an x-intercept at positive 2 here. Okay, notice it's going to touch here. And then we have an x-intercept at negative 2 and then another one at negative 4. We had a minimum at negative 2, 0. So this guy was a minimum. At negative 3, negative 25-ish. We're going to have a minimum. And then we have a maximum at negative 0.31 and 33. Now we also know something about the end behavior. So this thing starts out up here. And then we just connect those dots. Minimum, go up, maximum, go through the y-intercept, minimum, and remember this guy touches. So there it is. There's our graph. That's a quick sketch of what that guy looks like there.